Welcome to Smart Cap Teaching Online, which is proudly sponsored by Basic Education, VT Africa Holdings, Fibertech Distributors, and Vastra Tech. Okay, in order for you to be part of today's lesson or activities, log into www.hellosmart.com and then sign up as a guest. After that, type in your class ID, which is 59875. Add your name. Okay. So welcome back to Physical Science, grade 12, term 2. Today we are going to look at the conservation of energy. We are going to look at the conservation of energy. What I need you to expect. Vocabulary here. We have applied force, even though it's not new to us. Conservative forces is not new as well. And then friction is not new to us. Law of conservation of energy and non-conservative forces. If we can just look at this, we're just going to do this in detail today. Now, the table of contents, we have conservation of energy, the law of conservation of energy, conservative forces, non-conservative forces, and formative assessment. These are things that we are going to do today. I need you to get ready. Okay. Like I said, we are going to look at the conservation of energy. You have to ask yourself, what is it conserved there? This conservation is not new to each and every learner. This conservation, we talk about something that is going to remain the same. In other words, if it's not going to lose anything, it's going to conserve. And then that particular system remain constant. Okay, what about the energy? Energy, we know that this energy is its ability to do work. This one is responsible for carrying on with the motion or slowing down. When it moves on, it's gonna be the applied force to that particular object is in the direction of the motion. If it's opposing, where you can come across with the friction, is where you can just get a negative. In other words, we're going to come across with the positive net work done and the negative work done. It's not new to us. We were doing this before. What I need you to look at, we have the law of conservation of energy. Is not new as well. You came across with this in grade 10 and 11 as well. The law of conservation of energy says that energy can neither be created nor destroyed, but it can change from one form to another. In other words, you can't say I destroyed the energy. I can't say I destroyed the energy. We can talk about what we have here. This is we are seeing these notes here. There is energy that has been released. If you can just look at the light, there is energy that has been released. If you can just look at the lamp that we have up here, we have what? Energy has been converted electrons to light. That is why we have this. Okay. Now, in other words, don't forget, if they can ask you about the law of conservation of energy, don't forget that the energy that they're talking about, you can't destroy it. You can't create it either. So, but it can change from one form to another. Okay, we can just use the diagram here. I can see that you can see it clearly. Okay, let me make a full screen so that you can see. Okay, we can show energy changes in an energy flow diagram. This is the flow diagram when considering what will happen when an electric bell is made to ring. You can just have your own example. We can talk about a hood of a car if you want to, but here we're just using the bell ring. Here we have chemical energy in the battery. In other words, the energy that is coming from the battery is going to move through the conducting wires and give us what? Electric energy in the wires. This electric energy, we talk about the electrons that they are flowing along the wires or conductors. Then after that, we have kinetic energy in hammer. That the moment it hits there, it's knocking there, it's going to make noise. That is why that is a kinetic energy. The moment you have kinetic energy, you know that there is a motion there. It's not at rest. Okay. Then from there, we can talk about electrical energy in the wire, wasted heat energy in the wires, and then go. Okay, if you can just look at that, when the electrons flows along the conductors, there's a lot of energy just coming out. If you can just hold those conductors, after a while, you're just going to feel some heat on those wires. If they're not insulated, they can just transfer the electrons to your body and you get shocked. Okay, if you can just look at this, we have kinetic energy as well is going there because there is a waste of energy as well going to the heat energy in the wire and the gum. What about the useful sound? The sound that you hear, the other energy has been lost there to sound. In other words, you can't destroy energy and you can't create it, but you can just have the movement of energies from one form to another. All right, don't forget that this is very, very much important. I know that is not new to everyone, but now we have to look at the conservative forces. Wherever you come across with the conservative forces, you must know. Let me do something so that I can just highlight some of the things. Okay. All right. Let me take the full screen again. Okay. If you can just look at this, we have what? We have conservative forces. This is very, very much important because we are going to look at this. Whenever you come across with zero work done, you must know that the mechanical energy is conserved and then the work done is also conserved. If the net work done by the force, while they're moving an object around in a closed path. The closed path here, we talk about a loop. If we have a loop, you know that you start at 0 and go back to the beginning. If you can just look at this, let me just try to show you what I'm talking about. All right. Suppose this is the starting point. Suppose is the starting point, and then let me take this. You move from there, you just move around. Remember, this is how it moves. Started here. This is the beginning. This is the beginning of everything. Now you come here to the end. If you have this close, W then net is equals to 0. That is 0 joules. Don't forget, the moment you have this, you must know that you don't have a waste of energy. In other words, the energy has been conserved. The energy has been conserved. Okay. That is the closed path. Sometimes if you can just drop a ball, this is the height, you can just drop it. If the surface is smooth, it's gonna hit there and come back to the same position, then the net work done is gonna be 0 joules. In other words, we have conservative forces. If the net work done, this is very, very much important. We're dealing with the work. Wherever you come up with the work, you must know that there is a force behind it. Okay. If we have starting and ending at the same point. In other words, I showed you according to that loop, if you start from here, you end up here again. Work net is equals to 0 joules. There is nothing happened there. That is conservative forces. There's a condition. This condition is very, very much important. Don't forget it. If the net work done by the force is equals to 0, because where you have started is where you are going to end. Now, now you have what? You have conservative force. All right, this is a condition, it's very, very much important. Whether it's horizontal, whether it's vertical, I need you to think about that. Okay, according a common example of a conservative force, we can talk about the force of gravitation. This is an example of conservative force. When you come across with conservative force, you must know that we are talking about the force of gravitation. The force of gravitation, if I hold this pen here, I just hold it, it's only the gravity. The gravitational force is the only one force that is acting here. If I drop it, now it's just moving from the initial point to the final point. In other words, we have initial velocity here and the final velocity here. Up here, we have a maximum potential energy. The moment you release it, it's going to move from potential to kinetic. Okay, it's where you can just see the pen moving faster and faster until it reaches the ground. If it's not coming back to the starting point, you must know that it's not a conservative force. All right, whenever mechanical work is done by the gravitational force, one form of mechanical energy transfer. It's what I was just talking about. You move from the potential energy to kinetic energy. Once you reach there, you are going to have what? A zero at the bottom, zero potential energy at the ground. When it comes up to the highest point, it's where you can just get the potential energy. And that potential energy is there because of the height. If there is no height on it, there is no potential energy. According to the formula of potential energy, we have the mg multiplied by height. Okay, don't forget that as well. That is why mechanical energy is transferred into another form. Into another form, we talk about we are moving from the mechanical, potential energy to kinetic energy. All right, thus the total energy of the object is conserved. All right, this one is conserved and the object does not gain or lose any energy. This is very, very much important. In other words, under the conservative force, there's no loss of energy. You can't lose any energy, and then you can't gain any energy. You're going to maintain the energy that you have started with during the system. Okay, now we have, I need you to remember the following. Remember that the network done by a conservative force is independent. This is independent of the path taken. This is independent of the path taken. If a conservative force is the only force acting on the object during its motion. All right, in other words, if it's only gravitational gravitational force that is acting upon a particular object, you must know that you're talking about conservative force. All right, the mechanical energy here, if you can just look at that, I just want to show you something. Mechanical energy of an object is conserved. In other words, when we talk about conserved, it's going to remain constant, remain the same. That is why mechanical energy is conserved. In other words, you are just going to have this path. Where you have started is where you are going to end. And then the W net is equals to 0. In other words, there is no work happening there. Thank you. All right. All right. Let us look at this example. Okay, consider the following motion of in the diagram. If you can just look at the screen there, we have this drawing here. This is the bar that I'm talking about. We are just dropping up there. In other words, this is the is where you can come across with the potential gravitational potential energy, and then down here you don't have what? You don't have a gravitational potential energy because you don't have height. But here we have height. That is where we have this change in x equals to 2 meters. If you can just look at this, that is how it moves. It goes to the ground. After the ground, if it comes back, obviously this motion is, the energy has been conserved. All right. In other words, the energy has been conserved. This one is called conservative force. If we have this, the ground is rough surface, of course we're going to have what? We're going to have a friction. Once you have a friction, the ball is not going back to its origin. Is that clear? If it's not going back to its origin, of course, the energy is not conserved. All right, it has been transferred to other forms of energy. All right, consider that the diagram there within the frictionless situation. If it's frictionless situation at the bottom there we have what? We have is friction. We don't have any force that is acting against the bar. All right, indicate the forces doing work on the bar. Okay, in other words, you have to check there is only one force that is acting there. That is the gravitational force. All right, number 2, indicate whether the forces is conserved and explain why. If we can just look at that before we do anything, I said earlier, if this ball is going back to its origin, now the energy has been conserved. Energy is going to be conserved. If it's not going back, because of the frictionless, we know that the ball will just, what will happen? This will go back to its origin. Now we are going to have what? The energy has been conserved. We have conservative force. Okay. All right. If you can just look at that, it's going to be easy. Let me look at that. We have only gravitational force. That's what I was saying. The force is not conserved because the definition of conservation force says that the force is conservative force if the net work done by the force is 0, while the moving an object around a closed path, starting and ending at the same point, the ball does not return to its original position. Therefore, energy has not been conserved because it went to other forms of energy. All right, I need you to look at this. This is the one that I was just talking about. If you can just look at this, if you want to indicate the frictionless situation, for frictionless situation, there's no friction then, there's no other forces acting against the bar. In other words, you have to keep on doing the same thing. That is the same force, the gravitational force that is going to act on that particular ball, and then down there, it will just go back. It will just go back. If you can look, we've been told, the moment it went back to the same position where it has been started, of course, that one, the energy has been conserved. If it's just going to hit the ground, from the ground went back up again, we know that the energy has been conserved. And then indicate whether the energy of the ball is conserved. We all know that I was just explaining the energy there is conserved because the ball will just go back to its position. If you can just look at this, same position. All right. I will try to move fast. That is the same gravitational force. We all know that if you hang something, everything that is acting, there is only one force that is acting then. That is a gravitational force. Don't forget that. All right. If you can just go down, if you go down there, the force is conserved because it went back to its position. All right. And then the network done by the force is 0, of course, it's what I was just saying. In other words, we have a conservative forces that are present there. The mechanical energy is conserved. In other words, the gravitational potential energy at the top is equal to the kinetic energy at the bottom. That is why we have mechanical energy. That's why we are saying mechanical energy is conserved. All right. And then I need you to move with me quickly. Okay. If you want to prove it, you can just use the equation of the work done. That is W equals to f of g changing x cos theta. All the time I was just talking about this theta. Irregardless of vertical, you must know that this one is equals to 0 all the time. It's equals to 0. Don't forget that. It's equals to 0 degrees. It's equals to 0 degrees all the time. Remember, we're dealing with this. It's only we have to choose which side is positive. If you are saying going down because it's positive there, then going up is going to be negative. You have to choose, okay, going down there, we are saying it's positive. If it's positive, we're just going to use this formula where you are going to have a 0 degree. You are going to have a 0 degree. Remember, if you go down, it's where we can just talk about, let me just show you something. In the Cartesian plane, I just want to show you something. Okay, if we have this Cartesian plane here, that is x and y. All right, if we can just look at that, this is the origin. If we are going towards right, this is positive. This, if we are going towards left, this is negative. If you look at this side, we have what? We have positive, and this is negative. But this time, we have to choose going down because we are not opposing the motion. In other words, you have to say, we are going to have only this. Let me show you something here. Okay. All right. If we can just look at that. Now our motion is going down, not up. Not up, not up. Because of going up, in other words, we have something that is going up now. This motion going down, we are deciding that is positive. Going up is negative. Don't be confused. If you have these two, you must know that according to the x-axis, we have 0, and here we are going to have 0 degrees. Your theta there is going to be 0 degrees, which is equals to 0 degrees. Down here, because of the minus, your theta here is going to be, your theta is 180 degrees. Okay, cos 0 is equals to 1, but cos 180 degrees is equals to negative 1. Don't forget that. That is why we have this. If we can just come up here, we are trying to prove, whether this motion is conserved or not. If we can just look at the work energy formula, that is the work done. Let me just, this is the work. Yes, this is your work, and we know that work is equals to the product of the force and the distance covered. If we know that formula, you can just come back here and say W is equals to F, that is sub of G, that is a gravitational force. In other words, this is the weight of a particular object. This time our object is what? It's bar. Okay, the distance there is given is 2 meters, and then the theta there, I said we chose that downward is positive. If it's positive, we're going to say our theta is equals to 0 degrees. That is why we have this 0 degrees. Suppose that bar has a mass kilogram, has a mass of 2 kilograms. Okay, if your mass is 2 kilograms, you are going to say 2 multiplied by 9. Let us verify this. Let us verify this. Is 2 multiplied by 9.8. This is the gravitational acceleration. It's approximately 9.8. Don't be confused about that. Multiplied by cos 0 degrees, which is equals to, I'm going to have 2 multiplied by 9.8 multiplied by 2, that is the distance covered, multiplied cos 0, which is equals to, that is 39. Because we chose that, that is why we have a positive here. Don't be confused. Where is it coming from? It's because you have chosen that downward motion is positive. That is 39.2. Okay, now after calculating that, you have to prove if you have that, because the other one is going down, the other one is going up, we're supposed to have the same work done. All right, downward, we got 39.2 joules. What about the upward? The upward, you have to look at this. If we can just go back to the formula of work, we have W, which is equals to F of G, change in what? Change in X cos theta. Your theta there is no longer 0 degree because it's changing the direction of the motion. The moment it reaches the ground, it's going to change the direction of the motion. In other words, if it's positive, going down, because we decided that going down is positive, of course, going up is going to be negative. That is why you have to go back and say, okay, if I need a negative done, what am I supposed to do? Of course, according to the x-axis, we have 0 and 180. That is why I decided to say theta is equals to 180. Now you have to go back to the formula and say, okay, my W is equals to the product of f of g, change in x cos theta. My theta this time is equals to 180 degrees. If you can just look at that, we are still going to use the same mark. Okay, we have 2 multiplied by 98 multiplied by cos 180, which is equals to negative 39.2. Why negative? Because it's changing the direction of the motion. Okay, that is why we have negative. After that, you have to say the W net, we know the downward work done is equals to 39, positive 39.2 joules, but what about the upward? Upward one, the negative 39.2 joules. You have to say W net is equals to the downward work done of 39.2 minus 39.2, which is equals to 0 joules. This is the 0 joules. Don't forget that this is very, very much important. Very, very much important so that you can see what I'm talking about. This is 0 joules. All right. I hope we are satisfied about this example, because you can prove it if it's going back to the same position. All right. In other words, I need you to remember this. Conservative forces are the ones that they have a 0 work done, 0 net work done. And then where you have started is where you are going to end. If you don't have these two, of course, is not a conservative force. It's not a conservative force. All right. And then the other thing that I need you to bear in mind, that is the only gravitational force that is going to act on any object that has been hanged or held above the ground. Okay. Now we are done with the conservative forces. We have to look at the non-conservative forces. If you can just look at this, that is non-conservative forces. Here I need you to bear this in mind. In other words, your net work done is not going to be equal to 0. That is the first. Secondly, the energy has been transferred to other forms. During this motion, mechanical energy is not conserved, because if I have the ball here, I dropped it down. If I have it, let me show you. Let me say I have this ball here. of any building that you can just think of. As it comes down, it's coming down to the ground. When it reaches here, the bar, there's a possibility that the bar there is going to be deformed for a while. It's going to be deformed for a while. Why? Because of the friction at the ground. There is a friction there. The bar will just stop a bit and it will just go back. It's not going to reach where it was started. It's not going to reach where it was started. In other words, if we have 5 meters high, and then when it goes back, just let me say 2.5. That is 2.5. If we can just look at that, it's not going to reach where it, in other words, you have to say the network done is not equal to 0. It's to 0. And then the height that the ball is going to take is not going to where it was before. That is why I'm saying the energy is not going to be conserved here. Okay. This. Let me choose. Come on. Okay. If you can just look, the if conservative is act on an object, the mechanical energy of that object will not. Okay, if we can just look at this, I talked about the gravitational potential energy, because when it comes to mechanical energy, you have to think about these two, because it's equals to the sum gravitational potential energy and the kinetic energy. So this is very, very much important. This is very, very much important. In other words, the mechanical energy is not conserved. That is the first thing. Secondly, then you have to say the network down is not equals to 0. Reason being that the ball is not going back to the starting point. Okay, I hope we're together here. A common non-conservative force, we know that we have friction. I tried to give you an example here. I said at the bottom here, we have what? This is a rough surface, it's a rough ground. If it's rough, this ball, when it reaches here, is going to be deformed a bit, but you can't see it. After that, it won't reach where it was because we don't have a spring there. All right, that is what I'm saying. It's either you can get to half of it or far less of that 2.5. Okay, it's because of the friction at the ground. In other words, other energy has transferred to other forms. It's either heat or sound. If you have a ball, you can hear a sound. When it reaches the ground, that is the energy that has been lost during the motion. Normally we call it a friction. Then is called, we say, is called dissipative force. Dissipative force, we talk about the loss of energy. All the time you lose energy. All right, dissipative forces convert mechanical energy into heat and other forms of energy. We talked about the sound. If you drop a bar, you can hear a sound all the time. When you drop it, you must know that that energy has been released to sound, and others is gonna be a heat then. If you hit there, you can just, when you hold there, sometimes you can just feel some warmth at the ground. Is the heat that has been transferred. That is the heat that I'm talking about. Or other forms here, we talk about the sound. If you drop the bar, you can hear the sound. Okay. All right. If we can just look at the non-conservative forces, then we are still there. Another type of non-conservative forces is applied force. This applied force is very, very much important because each and every object needs something to with. That is the applied force. You have to apply to a pen. If I have this pen, I push it, I apply the force. It's going to move to the direction of the force. Okay, that is the non-conservative force. Don't forget, we have friction, we have applied force, we have air resistance, we have this spring. Okay, and applied force is a force applied by one object to another, one object to another, one object to another. Consider this is very, very much important. An applied force here acts in the direction of a body. All right, the positive work is being done on that body. I can just take you back to that example of dropping the bar. We decided to choose downward as a positive. In other words, you're going to have a positive work done. That is what this means. Okay, and then remember, the system is going to gain more energy. In other words, that is the increase. This increases the body's mechanical energy. In other words, it's going to increase as time goes on. It's going to increase more speed. All right. If an applied force acts in the direction opposite to a body's motion, we expect the negative work done. It's what we talked about. When it reaches down there, it goes up again. It's where you can just get a negative work. That is why I said it's not going to reach the maximum. The maximum height is not going to be reached by the motion of a ball when it reaches the ground that is not frictionless. Where there is a friction, it's going to stay a bit. After that, it goes up. And the sound there is going to pop out. All right. We talk about what? We're talking about a negative work. This is the negative work. This is the negative work being done on the body. This decreases its mechanical energy. All the time, when we talk about mechanical energy, earlier here, let me just go back a bit so that I can talk about this while you are seeing it. Okay, the mechanical energy there is going to change, decrease. In other words, if we started with this 5 here, of course, sorry, let me just take a pen. Okay, your EP is equals to, let me say, this EP is mgh. Don't forget that. If you have it there, the first EP is greater than EP here. I hope you are still together here. mgh. In other words, the mechanical energy is going to decrease. When we talk about the decrease of mechanical energy, I need you to think about the potential energy. Gravitational potential energy, because of the height, has been reduced. Of course, we are talking about the decrease of the mechanical energy. Because here, of course, we're going to have less kinetic energy. That is, EK at the ground is going to be less as well, which is equals to, when we talk about only, it's going to be less. They can't be the same. Let me say this is one, EP1, this is EP2. If you can just look at that, I can say EP1 is greater than EP2. The EP2 here, I decide, suppose here we have EP2 so that you can see the difference. This is EP2 because we have this less height compared to the EP1. Of course, whatever that you're going to get is going to be less. All right, now when we talk about mechanical energy, if you have less the gravitational potential energy, of course you're going to have less kinetic energy. That is why I said we have a decrease of mechanical energy. Don't forget that. That is the decrease of mechanical energy. Mechanical energy is nothing else. We talk about the sum of the gravitational potential energy and the kinetic energy. That's it. All right. In both these cases, the body's mechanical energy is not conserved. Thus, applied force is a non-conservative force. All right. I hope we are still together here. I hope we are still together so that we can just understand as we move forward. Okay. If we can just look at this, this is an example that we can just look at. All right. Let me give you only 2 minutes, or let me just work this out with you so that we can finish, in time, because we are left with only 4 minutes. Okay, as an object moves, either its total mechanical energy is conserved, or mechanical energy is transferred to non-mechanical forms, such as the thermal energy. We have a thermal energy, light energy, electrical energy, and so on. Whether there is an energy transferred or an energy conservation depends on whether or not external, we talk about the non-conservative forces are doing work. Okay. If external forces, we can talk about the applied force, we talk about air resistance, tension, friction, etc., etc. The external forces are doing work. Then the total mechanical energy of the object is not conserved. Yes, we know that. Energy is transferred between mechanical and non-mechanical forms. It has been transferred to mechanical and non-mechanical form. Non-mechanical one. However, if external forces do not do work, the total mechanical energy of the object is conserved. All right, true or false? The following forces type are conservative forces. We have this force of gravity. We all know that this earlier we talked about the conservative forces. The well-known force that is or known by conservative force is gravitational force. This one is correct. All right. What about the spring then? We have this spring here, because if you release it, when you release it, it will just come back to its original, to its position where it was started. Okay, this is correct. Non-conservative. Let us look at the non-conservative given here. We have what? Friction. We know that. I gave an example of the bar reaching the ground, where the ground is not smooth at all. It's where you can come across with what? With the frictional force. It's going to oppose the motion. It's either holding it a bit so that it won't reach where it was started. Okay. And then, yes, this one is correct. Air resistance. For air resistance, if you have, let me give an example. If you have a parachute, you just come down. There is air there, as there is air resistance. But remember, it's going down there, it's just opposing. Okay. What about the applied force? Let me say an object here, you just push it. If you push it, you have applied force. It's still a non-conservative forces. These, all of them, friction, air resistance, we have applied force, all of them, they belong to the non-conservative forces. What about the tension? The tension also, because it's very, very much important, is also part of non-conservative forces. All right. In other words, the conservative forces given there is correct. The non-conservative forces given there is also correct. What about the answer then? The answer is A. The answer there is A. All right. The answer is A. All right. The answer there is A. If we can just look at that, because all of them, I try to explain the gravity is only conservative force that is acting to each and every object being hanged or held or above the ground. And then the spring there. Don't forget, if you have a spring, you release it to come back again to its original position. That is why I said it's conservative forces. And the answer there is A. All right. Okay, even this one, I will just try to move fast. Is the following statement true or false? If gravity is the only force doing work on an object, then if total mechanical energy is conserved, of course, because there's only one that is acting on a particular object. The answer there is going to be A again. Don't forget, you have to think about this. I don't want to do this again on Monday. All right, let me finish this. If you can just look at this, this is your homework. This is your homework. This is your homework because of time. If you can just look at this, if both conservative and non-conservative forces are doing network on an object, then once the one can predict that the total mechanical energy of the system will not be conserved. This is your homework. I will give you the answer on Monday as we are finishing the work done by non-conservative forces. Thank you for today.